thank you for the organizers for inviting me to this series of lectures. The title doesn't tell much of things, it's quite generic, but this is related to bilinear Hilbert transforms. And all of what I'm going to talk about this day and the two following ones is joint work with Marco Olli and Christoph Thiele. And okay, I will present the proof of a theorem of ours, which is generalization of uniform bound for bilinear Hilbert transform. But I will present this new proof in the classical setting of an old theorem. So I will basically prove a theorem of Lacey and Thiele using a proof of ours of a more recent result. And all of this can be found in an expanded form in two papers by myself and Marco and Christoph, which have appeared last year and this year. Okay, so let's start. Okay, now it seems to so it was the first one. Okay, so let's start with the introduction. So what is the bilinear Hilbert transform, in case you haven't seen it? So it's a bilinear operator, so we take two input functions from, say, the Schwarz class, or, okay, I don't want to go to technicalities, so as good as you can imagine. And then we take a parameter, which, okay, to start with, let's take it to be a real number. And then we define the bilinear operator, VHTS, as this principal value. And now if you just forget the other function g, you see that this is just the Hilbert transform up to multiplication by constant acting on reflected f. So this is just the Hilbert kernel. And now to make it a bilinear operator, we put here the other function. And now it's important to choose this slope function, slope number s here in some way. And there are some special cases, which are called the degenerate cases. So if the s is 0, this g function doesn't depend on the integration variable t at all. So we can pull the gx out of the integral. And in that case, the bilinear Hilbert transform reduces to g times Hilbert transform f. There is another special case, s equals to 1. Then we see that the x plus t is inside both functions. So we can see that the bilinear Hilbert transform is actually just the Hilbert transform acting on the product of two functions. And this is again a case which we perfectly know, provided we know everything about the Hilbert transform. And then there is a third case, which is denoted by s equals to infinity, which of course you have to interpret correctly. So this is the case where we do the change of variable, ts equals tau, so that we get fx plus tau over s and gx plus tau. And when we send the s to infinity, we see that this is somehow the first case, but the roles of the two functions switch. So in this case, s equals to infinity, we again get f times h of g. And now in these degenerate cases, we have the theory of the Hilbert. So in the second case, we just apply the bound in LR, and then we apply Hölder's. And that's done. In the other two cases, we just apply Hölder's inequality and the bound in LP or LQ, and everything is done. So these are the cases where the bilinear theory is just Fubini's theorem, and the linear theory called the Hilbert transform. But of course, having seen this, you can start asking that what happens if we put here some other s. because then, yeah, it's not so clear how this should work. And this is the hard question, which was an open problem for a long time, but then it was solved by basic. But of course, before going to that, I would like to remind you about the historical motivation for this question. And this comes from something everyone in my current hometown loves a lot, the Cauchy integral along Lipschitz curve. So the original motivation for studying the bilinear Hilbert transform, the one that Calderon had, was related to the Cauchy integral on Lipschitz curves. And now here, to introduce the second object, we first take a differentiable function whose derivative is bounded, that is a Lipschitz function. And then we look at its graph and we interpret the R2 as the complex plane. And then for some nice test function, we just write this kind of Cauchy integral. And this is the same Cauchy integral using complex analysis, provided you put gamma to be some nice loop. In a way, this is a loop on the Riemann sphere. And of course, if you were in the setting where your function is analytic, okay, it's not possible with the assumptions I made, but this would be kind of giving you the identity. But now, in case you start with something defined on the curve, and you write this integral down, you will get something analytic in the interior of the thing. You can also go to the boundary and define a principal value. Then you have perfectly well-defined operator on the boundary. And yeah, without giving much more details, this object is of very much interest in complex analysis. It's somehow similar to the Poisson integral. So there is huge block of literature studying how to do the harmonic extension, what are the tangents of limits, the convergence of Fourier series, all these kind of things. But now for the Cauchy integral, you have again the same stuff going on, and it's important. Okay, so now Calderon was interested in proving L2 bounds for this object. So you take functions that are in L2 of the Lipschitz curve, and you would like to say that this Cauchy integral is again L2 on the same Lipschitz curve with the bound. And the first strategy he took, which was actually a very bad one, was as follows. So first, you just take a point on this curve, and okay, there should be some principal value, but we only. You first write this integral formula down, you just insert in this back. Then you write the complex half integral in a proper way, parameterizing the curve. So we will get this expression. And then you just say that this guy upstairs is my new function g, and I'm left with this denominator here. And now suppose the Lipschitz constant were smaller than 1, then I can write this kernel as a geometric sequence. And now you can ask that, okay, if I don't know how to attack the full Cauchy kernel, I can try to first look at these terms one by one. Okay, maybe it's easier. It turns out that it's not, it's way more hard. And now, taking one single term here, we define the Calderon commutators. And now the idea is that, okay, suppose you bound all the Calderon commutators and you get some decay in the order, then you would pretty much bound the Cauchy integral. Sorry, no problem. I'll be waiting a second. Okay, so then let's move to the Calderon comutator. So okay, there are operators for all values of n, but let's look at the first one. So now, when we want to bound the operator, we can look at the duality form. So we multiply by the dualizing function, and we would like to bound this form. Now, inside the Calderon commutator, because this A was a Lipschitz function, it's absolutely continuous, and we can use the fundamental theorem of calculus to write the difference as this. And then when we do some change of variable, we see that this expression is exactly the bilinear Hilbert transform of f a prime times the dualizing function. And now you see the bilinear Hilbert transform has appeared. And then the guess of Calderon was that, okay, maybe this thing is bounded. So suppose you can bound this BHT uniformly in S, then you just apply Hölder's inequality and the things follow. Okay, this turned out to be way harder than the origin. So then Calderon and others, they didn't pursue this thing. They found better ways, which I don't remember anything now about. We let them go. But returning to the Calderon commutators, there were several things in this Calderon strategy which are somehow suboptimal. First, in this very last step, what appeared in the computation was average in S of this operator. So such an average philosophically should be a nicer operator than just taking pointwise supremum of S. And somehow these averages can be treated with slightly different arguments than the bilinear Hilbert transform. And there is a nice exposition on this theme in a series of 3 papers by Camille Muscal, which is in Revista Mathematica Iberonica. So this was the first thing. To do Calderon thing, you don't do uniform bounds, you could do the average. Second thing is an interesting observation by Joan Barbera that if you want to found the Cauchy integral of Lipschitz curves, and now this strategy of Calderon, you have all these Calderon commutators. It actually happens due to a computation, which is in Barbera's paper, that if you control the first Calderon commutator, that is enough to control all the sums. So all the magic lives in the first Calderon commutator. So in that sense, the bilinear Hilbert transform is the fundamental object for this question. And then maybe just a remark, I have now given a motivation for the bilinear Hilbert transform by connecting it to the history of Cauchy integral on Lipschitz curves. But now the proof I'm going to present is leaving exactly this case out. So we will be working in a different range of exponents, but okay, it's still the same. Okay, and now let's look at the theorem, which is the old theorem of Lacy and Thiele and also Grafakos and Lee. I state just one theorem and many names, and people have done different parts. So let's start. The theorem as written here is the one by Grafakos and Lee. So if you take 3 exponents in the local L2 range, so that they satisfy the Hölder scaling, then for these exponents, there exists a constant C, so that for all S and all test functions, you have the Hölder type. And now this Grafakos-Lee thing was posterior to Lacy and Thiele. And what Lacy and Thiele did, this was somehow the first breakthrough which started this business, was that they proved the same theorem but with different order of quantifiers here. So they said that given these numbers and given S, there exists constant C depending on S. So this is a bound which is not unique. And now this update by Grafakos and Lee was to changing the order that given these exponents, there exists one C which works for all S. And this is why it's uniform. Okay, and this range of exponents, it's not optimal. I don't remember what is the optimal thing. I just know that it's proved. So there was a partial result of Chao Chung Lee, who's the same Lee as here. And this is something like, I don't remember the year anymore. But then the full range of exponents was finally proved by Uraltsev and Varshawski in very recent, I think 22 of the archive date, and it's not published yet. Okay, it's.
So when you say full range, R is greater than 1?
That's a range that I don't remember. So it's not 1, but you can draw a picture or kind of diagram of values of P, Q, and R where the uniform bounds.
That's known to be sharp.
And that is known to be sharp.
I see, because R equal to 1 is definitely not true. So
yeah, it is leaving much stuff out. But yeah, it must have somehow symmetry with respect to permutations of these 3 functions and somehow.
Oh.
Because it's uniform in S. Somehow when you rotate the S, so the line, these functions must be remaining invariant on the permutation. But yeah, it's not the obvious range you would say full range. It's the one that's known and that's not written. Okay, but for these lectures, we refer
sorry for interrupting, but maybe at the extreme point, so not R equal to 1, but R equal to something, maybe there is a weak result, or
okay, so,
again, I shouldn't test. Is it?
I think there are studies on the endpoints of these ranges when you are not talking about uniform bounds. I think Francesco Di Plinio with Thiele has something, and maybe some other authors. I don't have a good.
Okay. Right.
But yes, for sure you will find that branch of research that the endpoints. And okay, maybe I should still mention, if you don't look at uniform bounds, so you just take one S and you would like to ask what are the things, where can I go? Then this R, I think it's known down to 2/3 or something like that. And that limit is somehow, yeah, it goes out from the Banach space range. I'm not expert on that stuff, but you can go very down, and then it's really not known to be sharp, but on the other hand, people have no idea how to go beyond. It's just somehow the border of knowledge. All we know how to do breaks down at that. But okay, I would like to stay now in local L2. So for me, these numbers are always strictly, okay, this is now included, but I will exclude it in focus. Because now the point I would like to focus more than the exponent is the geometry, the value of this. And of course, now, as I said, the bilinear Hilbert transform in 1D, it's completely sorted in this instance. So when we talk about uniform bounds, everything is known. So now the next thing to look at is, of course, what happens in the plane. So we would like to study similar objects in the plane. And this study was started by Thiele and Demeter in 2010. They defined so-called 2D bilinear Hilbert transforms in the following way. So you take again 2 test functions. Again, you will write the product with the Calderon-Zygmunt operator acting on them. And now you do different linear maps here. So not just a constant, but the linear map. Okay, I think this is in a way the most complicated thing you can imagine in the plane, and also the most natural. And now for this operator, which is 1 dimension higher, there are again special cases and not so special cases. So first of all, if you put A and B to be one of them 0 or put them equal, you can reduce the questions again to study the two-dimensional Calderon-Zygmunt operators. And then there is a statement in Thiele and Demeter paper that, okay, if A and B are regular matrices, invertible, then things are not more complicated than what happens in one. Okay, that's kind of a brave statement, and it's certainly not easy to verify this for non-experts, but they give some sketch and they state it, and in a way it's true. And then the thing that's interesting in dimension 2 is that if the matrices are irregular, so that, okay, you map the plane to some line, these operators become really, really weird. And this was the main object of interest in Thiele and Demeter. And okay, I think they listed 6 cases, they solved, proved 5 of them. Then the last one was solved by Debeslav Kovac. And okay, all this study led them to introduce what is called triangular Hilbert transform. And that one is the big open problem for this. But okay, now when we have this setting in the plane, we would like to start studying uniform bounds there. So we would like to fix a class of matrices A and B, and we would like to prove bounds which do not depend on these matrices, just on the class we choose. And these weird objects I mentioned, the weird ways to degenerate, the triangular Hilbert transform, these are somehow ghosts which are haunting there. That if your class of matrices can move too much, these objects will come close to you. They will tell you that something bad will happen. And that's why it's natural to look at classes of matrices that are somehow restricted. We are staying away from the objects that are too bad for us. Okay, and now the theorem which is new that I just state for motivation, and in the simplest form possible, and in a form that can be found in our paper too, is the following. So we take a triple of exponents, all of them in the local L2 range, respecting the Hilbert scaling. And for this triple of exponents, we have constant, so that when we take any triple of non-zero complex numbers and any triple of test functions, we can look at this duality form of bilinear to the Hilbert transform with these 3 numbers or matrices, and we have the bound we are looking. And now, of course, I wrote this with complex numbers because it looks so neat. The point is that we can deal with all the conformal matrices. So when the class of matrices we take are the conformal ones, then we have uniform bounds. And somehow the conformal mapping has 2 things, it rotates and it dilates. And now the dilation part is the essential one here. So we can dilate these things with different pace, and that doesn't cause problems. And somehow, why is this not just a formal change compared to the 1D? Is of course that now the proof of bilinear Hilbert transform bounds is somewhat geometric. And now instead of using the geometry of intervals, we have to move to work with geometry of rectangles. And that's more. There are some technical pieces in the proof which really require new ideas. Okay.
So in the Demet theory side, if they consider, because this corresponds to the non-singular matrix case, so
exactly.
Even more than that.
Yeah.
So they don't have really like a uniform bound for a class of non-singular.
No, they don't. They state they state non-uniform they state non-uniform bounds, so dependency on the matrices when they are regular. But when these can be degenerate, for instance, becoming all the same. This is where their proof would have a blow up. Yeah, but for them, the main issue was that they were dealing with these 4 cases of singular matrices.
Yeah.
Okay, so now this is the thing, and now I will move to the proof. I will first give you short reduction to a bilinear Fourier multiplier, which has a line singularity. This is in the setting of bilinear. And this is the setup where we will work the rest of the time. And now the proof for bounding, the argument for bounding bilinear Fourier multiplier is, in our opinion, nicely decomposed in three parts. So there is the first part, which is the bilinear multiplier with point singularity. This is the part we will do today. Then there is the second part, which is the tree selection algorithm. So we will have a bilinear multiplier with line singularity. So we will decompose our function to wave packets, and then we will reduce our form to sum over wave packets, and then we will decompose the whole family of wave packets into what we call trees. And then the third part, which is the last lecture, is the part which we call the phase plane projection. And this last part somehow ties together this tree selection part and the classical bilinear multiplier. Okay, so let's start with going from the singular integral to the bilinear. Okay, so this is a formal computation that is easy, but it's nice to have. So first, when we write the duality form, we can just insert the bilinear Hilbert transforms. Then we write both f and g using the Fourier inversion formula. Then we will integrate away, we will do Fourier and integrate away, first of all, this eta variable, this x variable, and then we will see also the Fourier transform of the Hilbert kernel appear. So this is just distributing these complex exponentials in the right way. And once you have done that, you will see that you have three Fourier transforms, and then you have the Fourier transform of the Hilbert kernel here. And then typically, one likes to write this form in a symmetric way. So you have a Dirac mass, you have integral in R3, and then you write this thing as a Fourier multiplier depending on a third variable. But in the cases you care about, this zeta is not an independent variable, but it's depending on these things in this way. Okay, so now what we would like to do is to bound this form. And now we see that there is a multiplier. And sorry, I forgot to mention. Now we have this trilinear thing, but if we see what this trilinear thing means, it is the duality form for a bilinear Fourier multiplier. So we would like to study this kind of objects. So we take a simple function, and then we take the product of two Fourier transforms, and then we invert the Fourier transform. Okay, so you can also write it as in this form. This last formula is here just to emphasize the difference of the bilinear operator and the two-dimensional operator, because these are tightly related. So of course, if you are just looking at something two-dimensional, you would have here x psi, eta y, here would be x y, and that would be the thing. But now this bilinear operator is putting x and y here. Okay, and now for the bilinear Fourier multiplier, there are three special cases, as with the singular integrals. If the multiplier depends on just one of the variables, or if it's of tensor. So in the first cases, we just have the linear theory. And in the last case, we just do Fourier, and again, we apply the linear theory and Welder's. And somehow we run to the same thing as last time. There are other cases where you can't do Fourier, and then you must have another argument. And just to simplify the whole part of the matter, is that we can look at bilinear Fourier multipliers that are characteristic functions of sets in the plane. Now the cases that are easy, that are just Houdini, correspond to characteristic functions of Cartesian products. Okay, so if you have this thing, you just say that it's product of two functions, you do Houdini and you're done. And the interesting things are the ones that do not factor. So somehow any triangle cutoff is as hard as anything. And this is what we try to now do. It somehow looks it's strange why is it so hard, but the point is now that we are not just looking at functions in the plane, but we are proving bilinear estimate. And that's why rotations are forbidden moves in the Fourier plane. If you rotate this, this plane cannot be rotated as the normal part. Okay. So then, for the rest of today, I will now discuss the proof of this bilinear multiplier with point singularity. So this is the first step. In the end, we would like to understand the line singularity, but we will start with the point singularity. And now I will switch to black, and I think I should continue with other. Yeah, maybe I continue from there. So let's state the problem. So this was bilinear multiplier. This is too small.
I can see, but I don't know if what you think in the recording.
It's a bit too small. It's a bit small.
You can make it a bit bigger.
Like factor 3. Of course,
It looks
I will
fine.
start
I
like
think
this,
it will be
but
fine.
15 minutes past, we convert to this one. Okay. So. Okay, and now what we next discuss is a sequence of easier objects that we for sure know how to deal with. So first, if we take a linear multiplier and we take no singularity. This is an object that you to deal with even without having any background in harmonica. And the idea here is that you can just use the Yankee. So if I take a function phi, who is in L1, it is my kernel. And F within LP. This is the test function or the input function. Then the Young's inequality, of course, just tells you that phi involved with F is bounded by L1 or more phi times LP. Okay, so this is the case where no cancellation enters the game. This is a real analysis thing you prove by basically further inequality, not much more. And now what is the important example of this? Is the function whose Fourier transform is adapted to a ball. So we take a frequency and we take a radius, and then we say that M is adapted to a ball. In the following involves. And I give this example just to make you memorize the way I want to use the word adapted. So we want that the support of the function M is contained in the ball, and we want that the derivatives have the bounds we love. Okay, I didn't. And this should be bounded by R to minus order of the multi-index. And now I just look at multi-indices below some large number. This is not essential. And where do these adapted functions come from? If you take the unit ball and you construct some really standard function with the unit ball, for example, you take the standard multiplier in the unit ball, then you know that up to a constant, this standard multiplier is adapted to the unit ball. If the derivatives grow too much, you will divide by just some constant. You will get that it's adapted. And now, if you take some other ball, anything, you can push your function defined with the unit ball to the other ball by translation and dilation. And now if you had the absolute function phi in the unit ball, you can map it to something else in the other ball. And the mapping will be something like x goes to x minus y over r. And this is the way how you can always say that these kind of functions exist where you want. Okay. And what should I say? If you want to have a smooth function, we support it in this kind of set. These kind of derivatives are the best we can hope. And these functions are important for us for two reasons. So first, if f is adapted, then we have bounds for its Fourier inversion. And for this implies that adaptive function is equal to 1. I didn't think more than 2 seconds about if it's d or minus d, but okay, choose the correct one. Okay, and this tells you that adaptive functions go with Young's inequality. And where do the adaptive functions arise? The typical source of them is the Whitney decomposition. So, for instance, if we are having a point in the plane which we would like to avoid. So suppose we want to cover the plane minus a point with balls that have bounded overlap. Then we will do the Whitney decomposition. So okay, I just write here the schematic picture. So it looks like this. So these are the balls that satisfy the properties that the diameter of B is roughly the distance to say origin. If this point here is origin, then I want the family of these balls covered. And then I want that if I shrink them a bit, say by 1/5 concentrically, I will have these strings. So okay, this is very, very fast, but this is what needs to be. Whitney balls with respect to origin. And then we can talk about Whitney balls with respect to other points. And okay, how you construct them? Suppose you are in RT. For any point, you take a ball centered there with radius distance to origin over 1 million. You take all those balls, you divide your plane in the dyadic annuli. In each of the annuli, you apply the 5 covering lemma, which gives you this kind of family, and then you put the families together. You do some fine-tuning when the dyadic annuli are close to each other. That's how you get the Whitney balls. And once you have this kind of cover, you can form partition of unity there by the standard way. So for each ball, you map it to the unit ball. You create your standard function. You bring it back, you get something adapted, and then you do this standard sum of each of the functions over sum of all of them, which gives you the partition of unity, and then it's easy to check that you will have a partition of unity in the complement of origin, and each function in that partition of unity is adapted to a single Whitney ball. Okay, and okay, that's all we say in the setting of linear no singularity. So even if this is a trivial case to treat, the objects to which it applies are somewhat of fundamental importance. Okay, and then the next object is to move to bilinear. And we stay as smooth as we were. So now if you look at the Fourier side, we will have a smooth function. And the product. And again, if we were just doing two-dimensional instead of bilinear, it would be exactly the same. But now we want to do something bilinear, and even no matter how smooth this thing is, it doesn't mean that it would flatten, because the function it might have support like this. It's still smooth, but it's very much not a rectangle. And even if the support were rectangle, it would be not a open support. And here the trick is to use Fourier series. This is an elementary trick, but it happens so often that if you don't know it, it causes a lot of headache. So if we take the multiplier n, suppose its support is here. K is now the support. So the idea is that we insert a square, which we call Q, that contains the support. And now we can say that M is equal to this thing. Because this characteristic function is 1 in the support of n. This is still not solving the problem because this is not the tensor of tensor. Then we take another set which is Cartesian product. Let's call this Q prime. And we expand the function m as Fourier series here. And then we get some of things which are on the third order. Yeah, of this way. And now the complex exponential is of course the function that tensors. So I see that I have now here tensor functions and a coefficient. And because this thing was smooth, like in this computation, I can get dk in AK. So if I want to compute what is the LP norm of this bilinear multiplier, I decompose it in this sum. I put by Minkowski's inequality the LP norm inside. I use the decay of AK because this is a Fourier series of smooth function. And then I control these terms one by one, and I have summability in AK. And by this Fourier series trick, you can say that a smooth bilinear multiplier with no singularity can be represented as a sum of tensor form multipliers, and there is decay in the summing parameter. Okay, so now up to Fourier series, this is just. And okay, I continue on this side. Okay, then this was bilinear and smooth. The third thing is the one we again know because it's from the linear theory. when we have the Mittrin multiplier times singular. Okay, here I need not say much because I think this is the thing everybody knows. So what is the Mittrin types singularity? What we always mean is that we take the simple function from Rd to say complex numbers. Then I want it to be bounded. And I want it to be smooth in the complement of my special point of origin. And origin is now the point where the singularity is supposed to be. And the point is that this is bounded function, but when you start differentiating, things can start getting and these kind of things are important when you, for instance, have the cutoff. Okay, and the Mittrin type bound means again the same as the adaptation, but now we are not restricted to any pole. So we say that when we take the derivatives of the multiplier, these are decaying as psi minus alpha. And again, I can put here the same amount of derivatives, which I trust to be enough. 100t. And now what is the important example of this? So we can go to weakly decomposition of the complement of the origin. So when we sum the partition of unity up there, we get 1. But now if we give for each of the balls appearing here a different number, they won't sum up to 1. It will be sum of adaptive multipliers, and that sum will be a Mittrin multiplier. It's easy to see that it satisfies this bound because when I take any point here, I will have the dimensional bounded number of balls that contain that one. And when I look at the bounds I have from the weakly cover, I will write them in this adaptive form, but now for weakly balls, this capital R is the diameter, roughly, which is roughly the distance, which is roughly this number. So this is where the Mittrin multiplier comes. And now to prove the Mittrin multiplier theorem, you say that in each of these adaptive balls, you have this bound here. Then you will sum just all the scales up and down. You will get the Calderon-Ziemann estimate, the kernel estimates for the kernel, and then you verify the L2 boundedness, and you will use the Calderon-Ziemann theorem to say that such a thing is a bounded operator. The important special case is the Littlewood-Payne inequality, where instead of this kind of weakly decomposition, you will look at annular decomposition of the Fourier plane. And there you can say that the square function is bounded by Mittrin multiplier up to a randomization. So you can say that the Littlewood-Payne square function is expected value with random signs put on this annuli. And when you do Fourier for the expectation and the integral in RT, you will see that you just have to use the mid-range multiplier bound to get a little more value. Okay, so this is all we want to say about mid-range type simulation. And then we finally get to the thing of today. So we have bilinear thing, and we have point singularity. So now the point is that we take multiplier, which is again RD cross RD, the complex numbers. Then we take these assumptions with D replaced to, sorry, RD replaced by RD cross RD. So R2. And okay. Now the game would be that instead of the 2D type bound, we would like to prove the bilinear. And okay, I will have the break in a few minutes. Before the break, let's just see why this thing is interesting. So, as I said, the stereotypical Miklin multiplier comes from the Whitney decomposition. We just put some sequence of numbers on these Whitney balls, it still remains bounded. And moreover, by decomposing the plane into conical regions or triangular regions, the essence of the matter is to just take for each distance from origin one ball. So in a way, I have a sequence of these balls, and here also I would have sequence of balls. And now if you try to say that I have a multiplier who is coming from summing up adaptive functions here, 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 all of them with balls. I could try to prove bound for some of things with these Fourier supports. And now you can say that, okay, we could first try to mimic this passage from linear to bilinear we did for the case without singularity. But now the problem appears that when we project these things to either variable of g or variable of x, we will see that maybe in one direction we will get a sequence of Whitney intervals. But when we go to the other direction, these balls are not avoiding origin at all. So the condition really fails in one of the projections. So if we try to just look at the projections, we don't get objects that we can handle. One of the directions we will lose the cancellation. And that's why we need some argument. And this was a theorem of Koisman and Meyer with this degree of sloppiness in terms of how many derivatives you need. So that's why these are called Koisman-Meyer multipliers. This number of derivatives you need in the Miklin condition, it was pulled down to n over 2 when d is 1, when n is the level of multilinearity. So you need not have two bilinear, you could have multilinear. And the sharp degree of differentiability was done by Tomita. I forgot his first name much later. Okay, but we are not needing Tomita's theorem. We will be happy with Koisman-Meyer. So this is the Koisman-Meyer multiplier. Maybe the thing to remember is that when I have these estimates for the multiplier. It's permanently in the setting of linear multipliers, and when you talk about bilinear multipliers, you have Poisson-Meyer multipliers. These are essentially the same things, you just put different types of estimates for them. And okay, let's have a break now, and we will conclude with 2 points.
Maybe also if there's any comment or remark before the break. So let's make a break of 15 minutes. Is that okay?